Welcome back. So far, I tried to help you to build a concept between internal energy, the potential energy coming from the plus minus charges, with any changes that you might have to consider in chemistry. So in order to estimate the level of energy you have coming from the charges, and also finding way to lower their potential energy to the new energy state, we looked at things like an atom compared to other atom, which one can be more electronegative and which one should be bigger or smaller size in neutral state. Also, when they gain electron, they seem to grow in size due to the more repulsion, and also that changes electronegativity. So we can also compare not only the valence shells but shells inside. Same manner, we were able to understand why electrons spend more time in the middle and form a bond, and that also ultimately causing electron shift to the more electronegative atom with a more attraction that end up making the more electronegative atom partially negative, the other one partially positive. And I see students understand it and remembering it as if the negative one is getting electron. That's the opposite concept. That's wrong. Because the electronegative atom accepted electron, it becomes negative. The negative one doesn't want to accept electron. It wants to donate away electron. So the reason the electronegative atom is partially negative is because it's accepted electron. It's not, it's negative, so it accepts electron. That's a wrong statement. After that, we were able to understand the interaction between molecules, like a water molecule having hydrogen attracted to the oxygen and the hydrogen attracted to the other oxygen in the water molecules, having some intermolecular forces. Then after network formed in the certain phase, the introduction of solute with a certain charge, partial positive, partial negative, then you would expect some rearrangement of water molecules. Say this guy here has to turn this way to bring partially negative oxygen closer to the positive, and probably this will also tilt a little bit more, and in the process you might end up breaking hydrogen bond, although you have a chance to make another hydrogen bond next to these molecules. So certainly you can imagine the mixing and dissolving process has breaking intermolecular forces and forming new intermolecular forces. Then we said when a certain molecule interact with another molecule, they can just have an interaction without forming, breaking, chemical bond. But some cases, you can actually form new chemical by breaking and forming new bond. Then we said that's because the original chemical as an initial has higher potential energy, meaning the nuclei in these chemicals are not able to stabilize the electron as good as these arrangement of the same atoms in different molecule. So when these are more stable, meaning more attractive for electron, less repulsive for atoms and electrons and neutrons and protons and so on, so the change will be spontaneous. So whenever you form molecules, you have to draw a structure such as this. And whenever you introduce new bond to the central atom, you have to consider repulsion between electron pairs. Then try to minimize the repulsion and put the electron where it feels most attraction within the bond. That way you can further lower the potential energy. So when you have 4 pairs, for example, it was best to put them in this kind of arrangement, and that's called the tetrahedral, which is like this. So you get 109.5 degrees of angle between all these lines. Then we went further, saying when you have more than one atoms, central atoms with multiple bonds, you get this kind of situation where you have to compare not only repulsions between these electrons, but also have to consider repulsions across the atom, here, and so on. And I said that's not easy to see the change from this perspective, so a scientist, his name is Newman, he suggested to look at the molecule this way. So when you turn, you can see changes easily. So in next couple videos, I'd like to talk about how to build a molecule, then how to draw the molecule. So let's practice building molecule and then study various ways of drawing it. So this is molecular formula: C2H6O. This means that 2 carbon and 6 hydrogen and oxygen form at least one strong sigma bond, then became one molecule. So for that, you can come up with a various arrangement of the 2 carbons, 6 hydrogens, and oxygen, and those different ways of connecting them, creating different molecules, and we call those different molecules isomers. So isomers are the molecules that had same formula but some difference in the structure. It's not always necessarily just connectivity. It can be more delicate small changes that makes them different structure. So we'll have some video spending more in-depth time on the isomerism. But today, as a beginning video, I want to suggest to start with something. It's not the unique only one way. I just want to suggest to begin with most multivalent atom. So in this case, as you know, carbon, oxygen as a second row elements, they can make bonds to fill up maximum 8 electrons. Hydrogen as a first row element, it only can accept maximum 2. When I say maximum, you don't have to fulfill maximum. It can hold up to the maximum. So third shell elements like phosphorus and sulfur and chlorine, they don't follow octet rule strictly. The octet rule is not recommended rule, at least in my class. It seems to only work best for the second row elements. It's 8 out of more than 100 atoms on the periodic table. So I go by the maximum possible. However, you don't have to fulfill maximum. It depends on given situation, and you only make it most stable by giving electron most attraction and least repulsion, and same for the nuclei. So let's start. Let's say you decided to put carbon first, then oxygen. Or you can start oxygen first, then carbon and carbon. But in real life, as you see, carbon, carbon, oxygen, or oxygen, carbon, carbon, they're same. So we ignore this one. Then what's other possible arrangement? Well, you can do carbon, oxygen, and carbon. Then you have to place at least one sigma bond to be part of the molecule. So I make a bond. Remember, there's no actual line between real atoms in molecule. It's just representation for us. So there is a circular valence shell here and here, and you find the more electron density there. That's what it means. I hope you can remember. Then you know one electron in this bond, according to some theory, belongs to this carbon, and the other electron here belongs to that carbon. And the bond here, same way. This electron comes from this carbon, and this electron comes from the oxygen. Same goes here. Then you have 6 hydrogens. In order to do that, you have to arrange the 6 hydrogen knowing the maximum number of electrons you can have and the typical number of bonds you make for each atom. So the carbon can have total 8 maximum. You don't have to, but you can. And it has its own 4 electrons in the neutral state, which is the case. So you start putting electrons like second one after this first one, then third and the fourth, and same for this one, 4, and then the oxygen has a 6 in neutral state, so 1, 2, 3, 4, 5, and 6. You already see 2 lone pairs. And same over here. 4, 1, 2 for oxygen, so 3, 4, 5, 6, and for that 1, 2, 3, 4. Then you add hydrogens with 1 electron in neutral state. So hydrogen, first one, bring 1, second one, bring 1, third one, bring 1, fourth, fifth, seventh. If you wonder why don't you put hydrogen here and the third electron, in the previous video I said by some rule any size of the bonding only can have 2 electrons at the most. And same here, 1, 2, 3, no more, 4, 5, 6. Then you know you already added all the 6 hydrogens and all the valence electron that belongs to these atoms. Then you have to double check whether you have the corresponding charges. Well, here no charges are given and we have no charges on the molecule, so this is right Lewis structure drawing. Then you can redraw these Lewis structures this way, converting 2 electrons into lines. And you have to leave the lone pairs as it is. For this molecule and for that molecule, converting all the pair of electron in sigma bond into line. There. So these two are 2 different structures you can come up with, and these are isomers. Now, when you apply the potential energy concept, this structure is not correct because the carbon, for example, has a 90 degrees for each electron pairs, and I described it in previous video. That's not stable. With the 4 electron pairs, you need to make a tetrahedral geometry for the electron pairs. So you've learned from general chemistry the VSEPR is using the electron repulsions to find the better 3D geometry. 3D geometry is important, like I described in previous video, that allows us to predict their physical, chemical properties in chemical reactions. So, if you have carbon with a 4 pair of electron, you have to demonstrate this shape here. and there are 4 bonds. And usually when you draw this, you want to have 2 lines parallel to you. Then you realize these 2 in this case are parallel to you, and this line here is coming towards you, and the other one eclipsed with this is behind, going away from you. So that is shown this way. Line, there carbon, then solid line representing these 2 parallel line, which is like a parallel to the paper. Then the one coming at you will be shown in wedge. The one overlapped, and behind this wedge line is the one going away from you. So that's what I drew for the first carbon over here. Then, okay, I should hold it this way. Then there is a second carbon. There is already one solid line for the second carbon, and in this case you have a second line coming that way, parallel one. This is a wedged one, and that's dashed one. But if you happen to hold it or spin the single bond freely, then you can have the solid line representing parallel to you to the paper upward. That's okay too. Then let's try that one. If you do so to connect carbon to the oxygen with the sigma bond, then you have this wedged line indicating the electron pair going up towards you, and the other one behind, overlapped, is the going away dashed line. Then oxygen has 4 electron pairs, but you only have, say this is holding hydrogen, only one more additional pair besides this sigma is in the bonding with in this case hydrogen. So I have 109, 109, 109, sp3, the tetrahedral arrangement of electron pair. Then what do you do with these? You show lone pairs this way, and you put the hydrogen here, 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 and here. That's your 3-dimensional structure drawn by VSEPR, which considers the repulsion and attraction, the potential energy. So this carbon, you can say, has tetrahedral geometry. That does as well. But we don't say oxygen having tetrahedral geometry. We say it's a bent geometry. However, the 4 electrons are in tetrahedral arrangement. The geometry is bent. Why? The geometry is something that we can see using such as X-ray crystallography. We only see the nuclei by diffracting some particles we throw at them. We cannot detect the exact location of electron. I hope you remember the uncertainty principle. So because we only notice hydrogen, oxygen, carbon, we see bent shape. But for carbons, you have 4 atoms around detected in tetrahedral arrangement, so we call the geometry around the carbon as a tetrahedral. Okay, so we can do this quickly for the second isomer. Apply repulsion from the Lewis structure, and you get the VSEPR structure to lower potential energy between these repulsive electron pair and this sigma, the lone pair with the sigma electrons. Say we start from oxygen. Oxygen can have, this time let me draw 2 solid line, parallel line this way, then you can imagine two lone pairs going in this arrangement of tetrahedral. And the sigma electron, again, they are in the middle-ish, but they are closer to the oxygen due to the more effective nucleus charge attracting electron to lower the potential energy, and they are on the second shell, right? Then this and this is actually this and this carbon. So you put the carbon. Then the carbon can have another solid line. Let me just randomly choose. This line is here, so 109 from there, from this angle is right here. 109 from here is there. So let me choose this one to be solid line. I'm just choosing randomly. Both are equally possible for now. Then in the middle of the two lines, you can put wedged line with the hydrogen, dashed line. Same way. This time, let me put solid line over here, 109 angle. 1, 2 more. So there. That's your VSEPR. So when you compare the informations in the Lewis and the VSEPR structure, they both shows number of types of atoms, and you can also see the types of bonds. In this case, you have only single bonds, but you can have a double bond and triple bonds shown in both drawings. Also, you can see number of the lone pair, and so on. However, the difference is the VSEPR has information about the angle. Therefore, you get more precise information about how close they are. Here, that information is missing. And later, when you do deeper chemistry, those information becomes very crucial. Alright, so we got two VSEPR structures with somewhat detailed informations about 3D. Then, in separate video, I like to discuss about hybridization, giving you more understanding, deeper understanding about the structure. The theory can even explain which carbon is more electronegative with the different hybridization, and thus the reactivity of each carbon can be explained. But now I'd like to go to the Newman. He said it's a projection, it's not real drawing. It has a little exaggeration and distortion of the information, but it helps us to see a certain aspect of the structure and allow us to evaluate the stability of the given structure better. But you're not breaking any bond. You're not allowed to. You're dealing with the molecule as it is, but you are making new looking by twisting around the single bond. Like I showed you earlier a couple times, instead of looking at this exact molecule this way, you see it this way. Then by turning it around, you can see the electrons are changing the relative location, thus they have different potential energy. And those different looking arrangement of atoms doesn't make them different compound. Actually, the molecule has enough kinetic energy most of the time, at room temperature even, they freely spins here, also here. Not only that, they have this vibrational motion going on. So all these structures you will see in a minute, they are found in the reaction flask. And these different structures are called conformation. So Newman projection shows you different conformation from different perspective without hurting molecule. So if I show you the given shown molecule as it is, it matches perfectly. You can pause video and compare. But he wants to show that you can make the best arrangement around every single bond, starting from this single bond. You can do it this way or that way. It doesn't make any difference. It's the same analysis to find the most stable energy state. You can do same thing for this bond from this angle or the other angle. So you can easily see, if you hold model in front of you, the given structure is not the best because you have these two electron pairs eclipsed. They're close. Other three other two, including these three pairs, repelling each other and try to go away if they can. But if you go this turn or clockwise turn, you can actually go away from each other. So that's more stable. So you found it. And here as well, that's already in the most stable form. So this overlapped one called eclipsed, and this one is called staggered conformation. So the best one is this around this single bond, and this for this single bond. So let's draw the Newman projection for the single bond between carbon and carbon. You can see only one circle, so I want to draw a circle representing the carbon, the front carbon. And you don't see the bond and you don't see the carbon behind. And you see only three lines in front, like this. But Newman projection must show those lines coming together. And the three lines on the carbon behind, you don't see the whole line. You only see the line going to the surface of the front carbon because the rest of the line is blocked, like this. Excuse me for the lack of the space up here. Then you can put the groups and atoms in the position. This is a hydrogen. I didn't put white ball, but I assume that's hydrogen, 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 and hydrogen. Then up here you have oxygen and hydrogen, like that. That's staggered conformation, the more stable one. You can do the same thing for this. But let's practice imagining the spin, because on the test or during the experiment or research, you don't always have the model in front of you, and also you have to practice and train your brain to be able to think about these simple rotations. So you can choose any carbon I showed you to turn around. So let me choose the front carbon to be turned like this, clockwise. But I don't turn 120 degree. I turn only 60 degree, which is half, and half. Then this hydrogen move to half of the 120, so here that moves to not there but half, there, and there, and they keep this angle 120. Remember what I said about Newman projection is not real drawing. In reality, the angle here is not 120. As you know, carbon has sp3 tetrahedral hybridization, so it should be actually 109. It's not really 120, but from this perspective, it looks like it. But anyway, you still have OH behind, and hydrogen here, and hydrogen there, and that's eclipsed conformation. Energy-wise, staggered is more stable in this particular case. So here you have a staggered, and there you have eclipsed, meaning by some reason after a chemical reaction or something, if you happen to form eclipsed right after change, then you know they don't stay like this. They will go spontaneously to the staggered, meaning the electron repel and try to minimize the potential energy by turning away to go to staggered. Or by turning the hydrogen front the other direction. I hope you can see that whether you draw this way or this way or this way, you know, any way you draw Newman projection, this way, they are anyway same compound. Okay? Okay, so you have to keep practicing until you see the Newman projection. You can still see two carbons there, one in front, one behind, and OH. So you should be able to come up with the equation C2H6O. Also relative locations of electron pairs, or even the charges, slight positive charge and the bigger negative charge and bigger positive charge, because these charge interaction will change the stability by some degree. Sometimes the eclipsed can be not as bad as a staggered. Depends on the charges you have on the group. You can imagine already. If you bring same charge, it's worse, like here. But if you bring opposite charges closer, then it's not too bad, right? It becomes more stable. So there are certain cases you have to look at the overall charge. I would say when you look at any drawing, you have to always look at the overall charges first, then try to analyze all the possible structures to see which one has overall most stable structure. Not just go by eclipsed is always less stable than staggered. Okay, so there is a way of drawing molecule differently. That's Fischer projection. This has more distortion of the structure. Thus, it's more difficult to understand. However, it's not too bad. First thing you have to do is you bring those staggered arrangements arranged groups to the eclipsed like that. So let me bring it to the eclipsed, and also here eclipsed. Then you hold it the way the top and the bottom groups away from you. Then those side lines coming towards you. So the vertical lines are representing the lines going away from you. Horizontal lines are bonds that coming at you in three-dimensional, but we're gonna distort it. So you're gonna flatten out the molecule, which is not natural. So I can't do it, but I hope you can imagine the flattened out structure, something like this. So if I copy this, you can see there's a carbon here, but you have line, right? And that line actually is going away from you here, and that also is going away from you. That's attached to the CH3, and that line going away is attached to the OH. Then those horizontal lines shown as a solid line in the Fischer, they're holding H and the H. So there you have a Fischer projection. Whenever you see the Fischer projection, it looks like it's a 90-degree, but it's not. That equals to the carbon holding two vertical lines that are going away, and two horizontal lines coming at you. If you see this molecule from under the table, say you are under the table, your eye is behind the table, okay? Not on the paper. This eye is under the table. Imagine this is table and you are under it, underneath it. And you see it from this angle, then in front of your eye you have a CH3. That CH3 is holding 3 hydrogens. That's right here, and that's the carbon. Behind that carbon you have the carbon holding 2 hydrogens and the OHs. That's the carbon behind this front circle carbon holding 2 H's and OH. And you can go back to the Fischer, to the Newman projection. If you have your eye above the table, not on the table, okay, above the table here, and look down, then you can see this carbon and this carbon overlapped. Now this carbon becomes front carbon. So we have Lewis structure, then condensed line and angle drawing, then you have Newman projection and Fischer projection. For the last, I have to add one thing. For the line angle drawing, you can omit carbon and hydrogens. So this structure here, you can just simply draw like this. For this structure, sorry about that, you can draw it like this, which means based on the total number of the bond that you can make for carbon, you need to know how many hydrogens are hidden. This point here, you have a carbon, which is this guy. The carbon makes 2 bonds, that's shown, so you know there are 2 hydrogen that's not shown. See, there are 2. This carbon has 1 bond shown, so 3 more there, so you have 3 hidden hydrogens. Same there. Carbon has 1 bond, so you have 3 hydrogens. Briefly, if you practice with this kind, you know, this carbon has 1, 2 shown, so 2 hydrogen. This carbon has 1, 2, 3 bonds shown, so 1 hydrogen. That carbon has 1, 2, 3, 4 shown, so no hydrogen, etc. So in summary, if you have to show big structures like this, you know that compared to this, that's more stable, because this one and this one, the electron pairs, they are on the same plane and they are eclipsed. If you finish the line angle drawing dashed wedged lines having hydrogens on it, and they're same for the wedged and dashed line holding, and looking from here, these are eclipsed, those are eclipsed, and they are eclipsed as well. Therefore, you have some unstable conformation around this bond. But these are all staggered. You have 2 hydrogens staggering to this, and the hydrogens are staggered to that. Even you have to imagine this hydrogen being either out or in, and then the lone pair in or out. So everything here, they are staggered and more stable conformation. And you have to know the single bonds are permitted to rotate using given amount of the kinetic energy. Certain repulsion they can go over, so they're constantly folding, unfolding within the boundary, and they're exploring potential energy surfaces to find the most stable one, but they have more existing conformation in the most stable with some less population in the less stable conformation as well. It all depends on the kinetic energy that's given, and that is important element when you start predicting chemical reactions. I hope this helps, and I'll have a couple more videos on structures. Bye.